Alright, hello everybody. This is Jake Smith here, and today I'm going to be talking about section 15.6, the triple integral. Now the thing about the triple integral, it looks a little intimidating when you first see some of these examples, but what we're going to see pretty quickly here is that it's really no more complicated than looking at a double integral, which again we can kind of break down further into a series of single integrals. Probably the hardest part for me at least is keeping all of these things straight. We're going to be dealing with a lot of variables here, and it's very important to kind of take it one step at a time, not get ahead of yourself, and pay attention to which integral you're working with at the time. So the first example I want to look at is here. And we see we have three bounds over on the left, from 2 to 4, from 0 to 4z, and from 0 to ln of x. And an important thing to realize with the triple integral, when you're given the bounds in this way, we simply want to work from the inside to the outside. So I usually draw these bars just like this, these brackets, just to keep myself straight of what I'm doing, and I can look at this as one integral at a time rather than kind of being intimidated by all this other stuff going on. And a tip before we get started too is you see this dy, dx, dz, and like I said, we're going to work from inside to out. It always helps to just label what your bounds are over here. I'll just draw it in at the bottom. So we have y equals 0 to ln of x, sorry. X equals 0 to x equals 4z, and z equals 2 to z equals 4. And it's pretty obvious to why we'd want to do that. First, we're going to be solving y in terms of x, we're going to solve x in terms of z, and then finally, once all of we've integrated in terms of z, we want to be able to get an actual numerical value at the end, which is what z equals 2, z equals 4 will accomplish. So let's just dig right in here. We're going to look at this first integral, the yellow zone here. And this, again, we're just going to kind of break it apart. Look at it as one integral, and we have x times e to the negative y dy. So not a terribly complicated integral. Remember, this is with respect to y, so we're going to leave our x as a constant. We could even pull it outside of the bounds if we wanted to. I think I'll just leave it there for now. That's fine. And so this one is obviously just going to be, again, x is constant, so we have negative e to the negative y times x. And those are on bounds from y equals 0 to y equals ln of x. Okay, so not terribly complicated here. Once we simplify that, what we're going to end up with is negative 1 plus x. Okay, so not terribly difficult here. And now what we really have here is this yellow zone was one integral, right? So just like the double integral, this yellow zone we have solved to equal this, right? Coming through here, solving your bounds, and ending up with negative 1 plus x. So what we want to do next is look at our x bounds, right? We solved that first part of the integral, the first integral rather, and now we want to look at part 2. So let's just bring our x bounds down. We got x equals 0, x equals 4z. And remember, we're integrating with respect to x, this blue area here. Okay, so pretty simple integration again, you know, just x minus 1, negative 1 plus x, whatever way you want to look at this. And what we end up with is x squared over 2 minus x on those same bounds of x equals 0 to x equals 4z. Now, because we're solving in terms of z here, what we're going to end up with for the solution to the second part of the integral is we have 4z squared over 2 minus 4z. And now again, that was the blue area of the integral, right? We needed the yellow one to solve this blue part. And now this is our solution to that second integral with respect to x. So we'll repeat that process one more time. Let's highlight that again. So now we're looking at the green zone, and this is just going to be an integration with respect to z. So we have z equals 2, z equals 4, 4z squared over 2 minus 4z, and again, integrating with respect to z. That should have brackets. All right. So from here, again, we got a pretty simple integration. We're going to simplify this 4z squared over 2 to, that's going to be, just reach our integrand here, 8z squared minus 4z dz. And this, again, simplifies to a really simple integral. We're going to end up with 8 over 3 z cubed minus 2z squared, evaluated over those same bounds of z equals 2, z equals 4. I'll let you work out that algebra. And what we come out to here is 416 over 3 minus 40 over 3, which is going to give us a numerical value of 376 over 3. So, like I had said at the beginning, we want to evaluate in those terms so that we can get this numerical value. And what this actually is, this is a volume of a solid, so it's going to be a real life number. It's going to be a real usable number in terms of having integrated. So one last thing I want to talk about here. I've got another example. And this one isn't quite given in the same way. We're given bounds, but not explicitly. Instead, we're told that it's over a region E. We're given the expression 6xy dv. And now remember, dv is going to be volume. So volume is x times y times z. So we know that this dv is going to expand out to dx, dy, dz, and not necessarily in that order. It can really come in any of many orders. I forget how many. But what's more important is what we're given as E. And they do give us bounds for E. We got x, y, z. And we are told E lies under the plane z equals 1 plus x plus y. So we know that that's going to be one of our z bounds, right? Our region isn't going to go beyond 1 plus x plus y. And now it's going to be above the region in the xy plane, bounded by the curves y equals root x, y equals 0, and x equals 1. And now, that was a little subtle, but I did just say in the xy plane bounded by the curves. So really we know, sorry, I totally lost my train of thought there. Let's just continue with the bounds here. So what we end up having is we get 0 is equal or less than x is equal or less than 1. And that's given by these bounds up here. And then we have 0 less than equal to y less than equal to root x. And we have 0 less than equal to z less than equal to 1 plus x plus y. So this makes it a lot more clear of how we're going to want to write out our bounds and dv over here. Like I said, we're going to have to evaluate dx, dy, dz, but choosing what order to do it in really comes down to looking at the variables over here. So let's look at z. Z is evaluated in terms of x and y. Now that tells us we're gonna want to have that come pretty early, because if you remember that last example, we eventually want to work out these variables, and then at the end we'll solve one of the variables, or rather integrate one of the variables, and end up with a solid number. And then again, y here, we're given in terms of x. X we're given in terms of numbers. So z has got two variables, 1, 2. Y has the one variable, and x has no variables. So that's going to tell us that when we solve this, we're going to want, this is e for now, 6xy. And again, we're going to want to solve dz, dy, dx. Okay, so now that we have essentially our setup, let's take a look at how this will all come together. So first we have bounds from 0 to 1, and that's x. We have y bounds from 0 to root x, and we have z bounds from 0 to 1 plus x plus y. That's still going to be our 6xy function, dz, dy, dx. Alright, so let's get this highlighter going again, and again, I'm just going to look at this as one integral at a time. Just make this nice and easy, huh? So, what we're going to end up with by evaluating this, well, again, we're integrating with respect to z, but there's no z in this equation. So it's going to make it pretty easy when one of the z bounds is 0, and this is all treated as a constant, because we'll have 1 plus x plus y times 6xy minus 0 6xy. So I'm just going to kind of push forward here, and we got still x 0 to 1, y 0 to root x. And then we're given 1 plus x plus y times 6xy. And that's already evaluated on the z bounds. So we'll drop that off. dy dx. Alright. Now, you can choose to pull out, like you could have pulled out the 6 and that kind of thing. I kind of like leaving it all together. I know it gets a little messy, but it helps me simplify when I start integrating other things along the way. And you'll see what I mean here. So now we'll look at the blue section. Oops. Integrating with respect to y. You get the idea. So y from 0 to root x. And when we expand out our previous function here, what we're going to get is 6xy plus 6x squared y plus 6xy squared, and that's going to be dy. Alright, well, looking at this, again, we're going to treat the x as a constant, just like the 6, and then we're just going to evaluate from root x to 0. So, our solution, I'll just write this out, 3xy squared plus 3x squared y squared plus 2xy cubed. And those were on bounds y equals 0, y equals root x. Okay, easy enough. Just like before, we're evaluating on zero bounds for one of them, so we can just multiply root x in for any y that we see, and that will be the evaluated version of this integral. So, we're going to have is 3x, that'll be root x squared, which here, I'll simplify these down below as we go. It's just simple x terms being multiplied root x. 3x squared root x squared plus, that would be 2x root x cubed. And again, that'll simplify to 3x squared plus 3x cubed, since that'll be x, plus 2x, and that x is going to be to the power of 5 over 3. Or, sorry, 5 over 2, not 3. Oops. So, yeah, that's 5 over 2, because we'll have that root x left over. So, oh, sorry, looking at this one. We'll have the x to begin with. X squared is going to give us, root x squared will give us x squared outside the parentheses. Then we still have one root x left over. So we essentially have x squared times root x, x 5 over 2. Okay, so we're almost there, and all we have left to do is integrate our x bounds. And thanks to that last part, all of our terms are x. So this is just going to be a simple power rule. And I'm sure we can all solve this on our own, but I'll just fly through this. So again, we still have x bounds from 0 to 1. 3x squared plus 3x cubed plus 2x to the 5 over 2 dx. Let's get a fresh sheet. Be sure to write any of that down if you need it. And that is going to end up giving us, again, just simple power rules for these integrals. Nothing too fancy. We didn't have to use integration by parts. We didn't even have to use a u-sub for these. So should give you a good idea of kind of how to work with your bounds to prepare you for the more complex integrals that we encounter down the road. And again, these are x terms, not that there's any variables left. Okay, and this is just some simple number crunching. Again, they all have x terms in them, and we have x equals 0 as our lower bound. So fundamental theorem of calculus, we pretty much just plug in 1 for each of these x's. We can evaluate that as the numerical value 65 over 28. So that's our answer. And remember what we started with. This was the triple integral. I'm just going to write our bounds again. From x equals 0 to x equals 1, from y equals 0 to y equals root x, and from z equals 0 to 1 plus x plus y, 6xy. And then that's dz, dy, dx. So just like I was saying before, since we kind of struck out each variable as we move through, we had an integral with respect to z. We simplified that to terms of x and y. We had an integral with respect to y. We simplified that into terms of x. And then we just had an x integral left over at the end that really was pretty easy to solve. And that's kind of been the experience so far, is that once you get to that last integral, it's all simplified down to the one variable, and it really takes out a lot of the legwork. So this has been my lesson on 15.6, the triple integral. Be sure to review the beginning of that second question. Setting up those bounds can be a little tricky, and again, you want to pay close attention to which variable you're integrating with respect to and in which order, because that's totally going to change the flow of how you go through this, and in some cases, if you set it up wrong, it's going to make it nearly impossible to solve by the end. So pay attention to your bounds, pay attention to your order, and what variable you're integrating with respect to, and you should be fine. So thanks for watching, and I hope you learned something.